Bam! Mr. True. In this calculus lesson, we are going to put another tool in our toolbox, and that is called the ratio test. We've been determining whether series converge or diverge, and we have looked at geometric series, telescoping series. We've used the p-series test, the integral test, the alternating series test, the limit comparative test, the direct comparative test, and now we're going to be looking at the ratio test. We need all of these tools. It's a difficult chapter, and these series can vary widely. We need all these tools. So we're going to be looking at a series that involves factorials or exponentials, a series that may converge very rapidly, and in that case, the ratio test may be very useful. This test is going to be used for finding intervals of convergence in a couple of sections, so we're not going to be just using this test, right now and kind of forget about it. It's going to come right back around and be really useful for us in the near future. The ratio test will be inconclusive, by the way, for any p-series. So what does this test say? Well, the ratio test says let a series, or the sum of a sub n, be a series with non-zero terms. So all the a sub n terms must be non-zero. Well, that series converges absolutely, that step above just regular convergence, if the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n is less than 1. Now, this series is going to diverge if the limit as n approaches infinity of that absolute value of a sub n plus 1 over a sub n is greater than 1, or if your limit comes out to be infinity. Now, if that limit ends up coming out to be equal to 1, well, then simply you've done some work, and unfortunately you have more work to do. This means the test is inconclusive. It doesn't mean that the series either converges or diverges. It just means that you'll have to try some other tests in our toolbox to take a different approach at it. Like, probably a pretty decent chance that maybe you could work with the alternating series test to see if the series converges, where this ratio test comes out to be inconclusive. Now, we're going to be doing 4 examples in this video. They're going to go from easy to hard. You might even know the answer to the first example before I even start, but that just simply means that you're noticing that the series we're working with is a kind of a special type of series, if you will, and we could approach or arrive to the answer much quickly. But then you'll see that the ratio test gives us that same conclusion, and maybe it just helps you understand that it works. Now, I'm not going to be working with a proof of this ratio test. You can find that in the appendix of your book or online if you like. We're going to follow this video up with a root test. That one's only going to have 2 examples in it. And then in the sections coming up after that, we're going to be talking about Taylor polynomials, Taylor series, determining, if you have, what are the intervals for convergence for power series. So we got a lot more coming up, even though we're nearing the end of this chapter. Let's get to that first example right now. For example number 1. And the directions are all the same. Determine if the given series converges or diverges. Well, we have the series where n starts at 1 and goes to infinity of 1 over 3 to the n power. Now, we're going to do this. We're going to analyze whether this converges or diverges with this new ratio test that we have. So with our ratio test, yes, indeed, it's true that, well, and of course, let's remember that if you're trying to determine if a series converges or diverges, it's always a nice idea to do the nth term test. I forgot to mention that at the beginning of the video. Just make sure that the limit as n approaches infinity of a sub n, let's make sure that that actually equals a 0, because if it doesn't equal 0, well, then it's automatically going to diverge, and all this other work is kind of pointless. Now, our first condition is that, all of our a sub n terms are non-zero, and indeed, 3 to any power, 1 divided by 3 to any power, this is never going to be equal to 0, so we've got that condition out of the way. We're going to be testing, or looking at the limit as n approaches infinity of the absolute value of a sub n plus 1. That means just take out the n and replace it with n plus 1. So there's our a sub n plus 1 term, the next term in our sequence. If you let that sequence go on forever, we have a series. But at any rate, we have 1 over 3 to the n. Well, of course, you have to be adding all the terms as well. But we have our limit here as n approaches infinity of a sub n plus 1 over a sub n. We're going to clean this up a little bit. course, we're dividing by fractions, so we're going to flip that bottom one up. I like to keep the absolute value symbols through all of these steps of my work until I get to the very end, just as good measure. Really, a positive 3 raised to any power are here numerator and denominator are 1. Neither one of these factors are ever going to be negative, and thus this term is never going to be negative. It's a positive times a positive. So the absolute value symbols here really, for this particular problem, are not necessary. They're redundant. But if there's ever any doubt, just leave them in there because you're guaranteed to be right. If you drop the absolute value symbols a little bit too soon, and by chance your expression here can possibly be negative somewhere, you're just setting yourself up to lose some points on a test or homework assignment or such that otherwise you wouldn't have missed if you just left the absolute value symbols in there. Now we have 3 to the n power, and we have 3 to the n plus 1. Just making sure that you understand here that just simply means exponents tell you how many bases you have, and n plus 1 means you have one more 3 in this base here, basically, is you have 3 to the n. Or you can write this as 3 to the n times simply 3. And when you multiply like bases, you add the exponents. You're going to be doing so much of this cancellation that you probably are thinking, why am I bothering taking time to do this? Or if you're a strong calculus student, you don't need to have that explanation, but some of us do. So we have 3 to the n in the numerator. We have 3 to the n plus 1. One more 3 in the denominator. Of course, all of these are going to cancel out, leaving you with one of those factors of 3 in the denominator, where I could have crossed out those 3 to the n powers there, and you see that is left. Now we have the limit as n approaches infinity of, well, it's just simply 1/3. And there's not even a place to, let n go to infinity in this expression, so our answer is simply 1/3. Now, remember over here when I was defining the ratio test, if the limit as n goes to infinity of a sub n plus absolute value of a sub n plus 1 over a sub n, if that limit is less than 1, well, therefore, by the ratio test, the given series, I like to just write it out, converges. Now, as soon as you saw this example up on the board and me saying, hey, I'm going to do the ratio test to show you that this, or determine, I already knew that, I was going to say show you that it converges because I already knew it converges, I made the example. You might have been saying, why are you even bothering doing all of this? Because another way of writing this series is to just say that it's 1/3 to the n power. I mean, yes, it says 1 over 3 to the n, but 1 to any power is still going to just simply be 1. Well, look at that. That is, a geometric series with an r value. Our r value is 1/3, and that is less than 1. So we have a geometric series with an r value that's less than 1, therefore it converges. Or we can do it with the ratio test. Now, with the ratio test, you can actually say it converges absolutely, or absolutely converges, because this is a test that will determine absolute convergence. So that is the end of our first example. Not very exciting, because we could have seen that it was a geometric series and knew from that knowledge that we have that it converges anyway. So let's look at another example, a little bit more interesting. So here for our second example, we have a series which is got -1 to the n power, which means as n goes from 0 to 1 to 2 to 3 that we're going to be alternating back and forth between positive and negative numbers, which maybe that means that this would be a good series to apply the alternating series test. But I also said with the ratio test, if you have a series that involves exponentials and factorials, look at there, a fractional exponent and factorials. So probably the ratio test is going to be very, very helpful to us and be my first choice to determining whether the series converges or diverges. So let's make sure that indeed all of our a sub n terms are non-zero. Yep, never going to be equal to 0. So that condition is met. We're going to set up the ratio test and look at the limit as n approaches infinity of a sub n plus 1. So we're going to take this expression, and anywhere there is an n, I'm going to replace it with, well, a sub n plus, or n plus 1. So we've got negative 1 to the n plus 1 power times 3 to the n plus 1 over, now here we have n plus 1 factorial, which of course is going to be n plus 2 factorial. Now that's our a sub n plus 1 term over a sub n. Just copy down what we have here. Now these absolute value symbols are once again going to take care of these negative factors. But again, I don't want to drop them. I'm going to leave these absolute value symbols through all of the work, even if I could say, well, we're going to drop these absolute values as we cancel out these factors, which is negative. But remember I said in a couple of sections we're going to be using the ratio test to determine intervals of convergence, and that absolute value symbol at the end is going to help remind you of exactly how to set up that interval. So just leave them in there. So we're going to bring up the denominator. And now we have to simplify this. Now I apologize if I spend a little bit too much time going over the simplification process. I don't know if you're an extremely strong calculus student and you just missed this lesson, or you like to learn online, you're doing some independent study, if your student really struggles. But I am going to take a little bit of time to talk about the simplification here. Of course, these exponents tell you how many of those bases you have, and we have n 3's in the denominator, and in the numerator up here we have n plus just simply one more. Or again, you can write that as 3 to the n times 3 to the first, and those 3 to the n's are going to cancel out. There's one more 3 in the numerator than the denominator, so this is going to cancel out, leaving you with just one factor of 3 in the numerator. Same thing with our bases of negative 1. So there's n of them here, and there's n plus 1 in the numerator, just leaving me with that one negative 1 in the numerator. Now our factorials. Hopefully by now you have gotten very used to expanding these and seeing how they cancel out. My pre-calculus students, even at the end of the year this year, are struggling with this a lot, so I'm going to show you that this n plus 2 factorial, of course factorials mean you count backwards, count down by 1 until you get to 1. So this is going to be n plus 2. Now reduce that by 1, so 2 minus 1 of course is 1. So on and so on. Just keep multiplying back until we get to 1. So factorial, like 5 factorial, 5, 4, 3, 2, 1. Stop, multiply them all together. Well, you see here, n plus 1 factorial is going to be n plus 1, reduce 1, n, reduce 1, n minus 1, and reduce 1, and reduce 1, until you get back to 1. So I can expand this n plus 1 factorial out, but I'm hoping that you see here that n plus 1 factorial is n plus 1 times n, and so on and so on. Keep counting back by 1 until you get to 1. So this n plus 1 factorial cancels out with this expanded notation of n plus 1 factorial, and we're just left with n plus 2 in the denominator. So now we've got this. Okay, well, as we let n approach infinity, we're going to have negative 3 over basically infinity, which means that this limit is equal to 0. Now 0 is less than 1, so therefore by the ratio test, actually, instead of just saying converges, absolutely converges. All right, third example coming up right now. Now our third example, well, we have a series that involves exponentials. And we dealt with exponentials. We handled them a little bit in the previous example. So this is going to be very similar. I don't have to worry about the negative 1 to an n or n plus 1 power. There's no factorial. So maybe in a way this is a little bit simpler, but let's walk through it anyway. So we're going to be taking a look at the ratio test again. All of my a sub n terms are going to be non-negatives. So set up that limit as n approaches infinity of 7 to the n plus 1, 3 to the n plus 1, plus 1 over 7 to the n over 3 to the n plus 1. The simplification process of all of these ratio tests you're going to be seeing in your book for this section are going to look very, very similar. We're going to be flipping this denominator up, and instead of dividing by that fraction, multiply by the reciprocal. Now, again, cleaning this up. Now, I want to point out a mistake, hopefully, especially now that we're in Calc 2, you're not making this mistake, but you know, I teach a lot of pre-calculus students and Calc 1. Make sure you don't cancel terms. This is 3n plus 1, and this is 3n plus 1 plus 1. So this numerator and this denominator have two terms in them. So don't be tempted to cancel this 3 to the n power with this 3 to the n plus 1. The only thing that's going to cancel here is that we have a factor, or many factors, but we have a factor of 7 to the n power, and up here we have 7 to the n plus 1. Again, there's one more base of 7 in the numerator than there is in this denominator, so we're going to cancel n of those out, leaving us with just 1, and we have this. Now, our factor of 7 is positive. We don't need that absolute value symbol to take care of that. Again, I leave those absolute value symbols in there to remind me that they should be there, not lose any points when maybe I've actually just sort of ignored them when they shouldn't have been, and also for helping me set up that interval convergence in a couple of sections. I just like to leave that notation in there. But we can take the 7 and move it out front. Okay, so we're looking at the limit as n approaches infinity of 3 to the n plus 1 over 3 to the n plus 1 plus 1. Now, what's that going to come out to? Well, maybe you know the answer, but we can show this limit notation, this limit work. Look for that largest power, and let's divide it out of the numerator and denominator. We're going to multiply the numerator by 1 over 3 to the n plus 1 power, same with the denominator. So, of course, anything divided by itself is 1. So we're going to change the look of this expression, but not its value. So we have 3 to the n over 3 to the n plus 1 is going to leave us with 1/3, because those n 3's are going to cancel with those n plus 1 3's, but leave us with one of those bases, plus 1 over 3 to the n plus 1 over, now as I sort of multiply this fraction and or basically effectively divide by 3 to the n plus 1, we're going to get anything divided by itself as 1, and then plus 1 over 3 to the n plus 1. Okay, double check my work here. Great. Now the limit as n goes to infinity, this is going to approach 0. So we have 1/3 plus 0. We have the 1 in the denominator. We have another term approaching 0. We have parentheses that are too big, and then ultimately you can see that we're going to end up with a limit which is equal to 7/3. And 7/3 is greater than 1. Well, that's certainly, you know, not inconclusive. Our limit is greater than 1, so therefore by the ratio test, make sure you tell your teacher and your test graders the test that you're using to analyze these series, by the way. The given series, the one with the original problem, diverges. It's our last example, and we have rather a scary one. We have the series here, the summation where n starts at 0 goes to infinity of n factorial over 2 times 4 times 6, dot, 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 and we're just going to keep multiplying all the way up to our nth factor of 2n. So basically multiplying a bunch of even numbers together. That looks quite a bit different than my previous 3 examples and probably most of the problems you're going to have in your homework, so it's kind of scary. But we do have a factorial in our series, so we're going to go ahead and try setting up for our ratio test and see what happens. Now, for the ratio test, all of our a sub n terms must be non-zeros, and this is never going to equal 0. So looking at the ratio test, we're going to be looking at the limit as n approaches infinity, once again, of our a sub n plus 1. And for our previous 3 examples, I've just taken out the n and plugged in n plus 1. But if I do that here, you might not see how the cancellation works. So since we're expanding the multiplication of all these even numbers, I'm just going to add on from the nth factor, the nth plus 1 factor. And that will help us see how things cancel away quite a bit easier. So here's our a sub n plus 1 over a sub n. Again, the simplification of all these ratio test problems is very similar. We're going to multiply by the reciprocal of the denominator. We're just going to distribute that 2 through there. And we have okay, and yeah, a lot of things are going to cancel out here. We have our n plus 1 factorial is n plus 1 times n minus 1 times n minus 2, dot, 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 down to 3, 2, 1. So instead of writing that expansion of really just n factorial, and I've already done that earlier in our examples, I'm just going to write n plus 1 times n factorial. And that's a little bit of an expansion of the numerator, and we can see that the n factorials are going to cancel out, leaving us with just the factor of n plus 1. And by not just taking this n out and plugging in n plus 1, we can see by adding the n plus 1 factor that 2, 4, 6 all the way up to 2n from the denominator here is going to cancel out with all of these factors in the numerator over here. And we get the limit, get a small piece of chalk here, the limit as n approaches infinity of just simply n plus 1 over 2n plus 2. And however you look at it, factor out a 2 from these 2 terms, use L'Hopital's rule, simplify this like we did in our previous example. The limit here is going to be simply 1/2, which is less than 1. So since 1/2 is less than 1, or it is, therefore, by the ratio test, the given series, I'm just going to write the given series, absolutely converges. This is the end of my last example. I'm Mr. Tarou. Bam! Go do your homework.